Hello, so today continuing on this weekly contest 323, the last problem, maximum number of points from grid queries. So we get a grid and by n grid as input and an array of queries of size k. And we want to find an array result or answer of that size where basically we take each query and we do the following. We start from the top left of the grid. And we keep traversing, of course, in these directions, up, down, left, and right, as long as the value is strictly greater than that. As long as the query value is strictly greater than the value in that cell, right? Once we find it's in one direction that its query is smaller or equal, then we stop, right? And as we go, we count the number of values that we find that verify this condition. And we call these points, right? So we just count them. And so for each query, what we want is the maximum count we can get respecting these rows here. And it says that you can visit the same cell multiple times, but of course you count it only once, right? And we want to return that result array, okay? So let's take a look at this example here. We have the grid here and we have these queries. So for example, let's start with 5. So we go for 5, we go here. 5 is bigger than 1, so good. We go here, 2 is bigger than 1, so good. So now we have 2. And then we go here, bigger than 5, we have 3 then. Here, 5 is bigger than this, that's what I meant. 4, 3, 5 is bigger still, so we have 5. And now if we try to go here, this doesn't work. If we try to go here, it doesn't work because 5 is equal to 5, equal to query. We can't go to 7 here, and we can't reach 1 because we stop here in this direction, we stop at this 5 in this direction, and so we stop here. So overall it's 5, so that's what we put here. For the second example where it's 6, similar thing, we will keep going all the way till here, we'll keep going all the way till here, so we have 3, 5. We can go to 5 because 6 is bigger. We can go here, right? So far we have 3, 5, 6, 7. We have 7, right? We can go here, so we have 8. But we stop here because we can't go to this 7, right? So overall it's 8. Yeah, and so you get the idea. That's pretty much it. We won't do the last one, but yeah, it's pretty much the same thing. In terms of time, in terms of constraint, we have 10 to the power of 5. The entire size of the grid can be up to that. And the queries can be up to 10 to the power of 4, right? So already this tells us that we can't do it per query. We can't do like for each query, do it separately and maybe do DFS on the grid. We can't do that because then that would be 10 to the power of 5 multiplied by 10 to the power of 4. So that's too big. So we need to find a way where we can do almost all queries in one go, right? So let's think about that. Okay, so let's see how we can solve it. So we have the grid here and the input that we get for the queries, right? Queries, let's call it Q. So how do we address this? So one thing you can notice is that, well, if, let's say we had this sorted, right, to 2, 5, 6. And let's say for Q equal to 2, we find that maybe, so for example here, maybe 3 are valid here. Basically 3 have Q bigger than them, 3 values or 3 cells starting from the top left. Then we know for 5 by definition at least it has 3. We don't need to go check again for 5 because 2 is smaller than 5, right? And 2 is bigger than all of these values. That means 5 is bigger as well. So we already know that we can start from 3 and just continue the processing. Similar thing for 6. Let's say we did the traversing for 5, just continued, and we found maybe that 5 has 5 for, yeah. So we know that 6 has at least 5, right? Because if they are smaller than 5, right, then they are smaller than 6. And so we don't need to go check all of these in both cases for 5 and 2. We can just use this 5 and build on top of it, right? So that's the idea. So we can sort the query first, sort queries first, then do the traversal. Now the tricky part becomes how do we not redo the checking, right? So now the trick becomes, how do we continue the processing from where we left off, right? In order to have this work properly and stop when we need to, what we can do is, let's just keep traversing, but among the neighbors always pick the smallest, right? So that this is ordered, and so that if it's smaller when we pick off, and we have the next value, we have a chance of finding the next bigger one that may be equal, right? If that makes sense. And so instead of just traversing the grid randomly, we'll add the elements in a priority queue. Basically, we'll add neighbors as we find them in priority queue, and we'll keep popping until it's no longer, the condition is no longer valid, this condition for the query we are at. Then once it's no longer valid, we will go to the next value, right? So that's sort of the idea. I hope it makes sense. Let me just do it again on an example just to make sure we really understand it. So let me just copy this here. Okay, and what we will have is, of course, we'll sort the queries. So the sorted queries would be 2, 5, 6, and we'll do, of course, BFS or GFS with the traversal. I'll do BFS for the traversal. Okay. And what do we want to count? We want to count how many we find that have these conditions that are it's actually this that are smaller than Q. Okay. So we'll count that. We'll start from 0, and then we need our heap, right here. So this would be the heap that will contain the values as we find them. And so we have our current count, and we will just keep push to the heap as fine. Of course, we need a visited set so that we don't visit twice. So let's just put that here, and let's start. So the first thing we do is we go here 1. So we need to add that first to our heap. So we need to add the first value 1. Okay, but we want to check the condition. So what we want to do is something like, we want to traverse the queries in, of course, sorted queries, right? And of course, we want to start our H with the first value. So that would be grid at position 0, 0. So we'll start with 1. But we also want the coordinates because in the traversal, we can go up, left, down, and left, right. And for those, we need I. So we need to do I minus 1j. We need to do I plus 1j, and you get the idea, right? So here we need the coordinates, right? So we start with that. And we know that we need to keep popping as long as there are values in our heap in this case. We didn't use a queue because we don't just want random traversal. We want to pick the smallest neighbor first. And we also want this condition. For each query, we want to keep this condition. What is that condition? It's just the smallest value that we'll extract first. We want it to be smaller than the queue. So we will do the smallest value smaller than the queue that we are looking at, right? Okay, so if it is, we can just pop it and count it, right? And go through the neighbor. So if it is, then we want to pop. So of course you do something like heap q, heap pop in Python. Okay, so we'll get the value, we'll get I and j, and then we want to count it because we just found it's valid, so we count it. Okay, so here we have 1, we count it, we have 1 now, and we pop it out of our stack. Okay, so let's delete 1, and now we go to the neighbors, right? And we add them all to our queue, right? So sorry, we can't go to 5. We have to go to either one of those 2 because that's the traversal we have. And so here, of course, we need to go through the neighbors. So that would be basically just for the neighbors coordinates, and you can imagine that can be just 1 plus j. You know how we know how to do that. I'm not going to spend time to that. And of course, if these are valid, the coordinates are valid and not visited, then we can add them to our heap, right? So we'll push them to our heap because we want to pick always the smallest one. So we'll push them to our heap. We'll push, of course, the value as well because we want to check it here. So we need to push the value at that position, and I and j, and push an I and j. okay? And we want to, of course, add to visited, but that's just the details of BFS, right? And so here we want to add these two, so we add 2, 2, right? And now we go again here, right? And we check, we pop it, we check if it's smaller. Is it too smaller than this query? No, it's not. So we stop, right? So we stop, we exit our while loop and go to the next queue. But notice here, our count is still 1. We keep track of the one we found so far because the next one is has the previous one smaller than it because it was smaller. 1 is smaller than 2, it's smaller than 5. We know that already, so no need to go back and check 1 again. So we are not going to check 1 again. We are just checking our heap. It has 2, of course, with the coordinates. And so is this, which is this 2, so with the coordinates, what is this, 0, 1, 0, 1. So 0, 1 here, it has, of course, 0, 1, and this one has 1, 0. So we'll check this one. Is it smaller than the new Q value, which is 5? Yes, it is smaller. So we can pop it. Let's remove it. And we increase our count because we found another one that is smaller. So now count is 2. And we go through the neighbors of this 2. So we go here, and add them. They are not visited yet, by the way. So 1, 2, this is 0, 0, and this is 0, 1. This one has been visited, so we add it. 3 and 5 are not visited yet, so we add them. I'll keep track of the coordinates just abstractly, but we don't need to type everything here. Okay, so now we go through the heap again. It still has the top value is still, the first value is still 2, the beginning of the queue or of our heap, the smallest value in the heap is still 2, is this 2 here. And so we check it's smaller than 5, yes, and so we pop it off again. And of course we visited it here, so we add to visited here. So now we have this one in visited, we have 3 in visited, we have 5 in visited because we already added them. So we add to visited here, add to visited. Okay, so now we processed that one, we counted it, we need to count it because we just extracted it. And then we go back again, smallest value is 3. So that's what would be in the beginning always. And so we check, is it smaller than 5? Yes, it is. So we pop it off. We increase our count again to 4. Okay. And then we go through the neighbors of this 3 here. So 7, 2 is already visited, so we don't add it, but 7 is not, so we add it. Okay, so now it's added here. And again, we pop the smallest again, which is this 5 here. So we increase our count now is 5. And we visit the neighbors of 5, which are this one and this one. 7 is already visited, but the second 5 is not, so we add it. And you get the idea. We keep doing this until we are done. For 6, we will find that we already have the 5 already that we have, so we'll just continue with the current heap of with the neighbors that we have, right? So I hope that makes sense. Heaps allows us to get the smallest one, so we guarantee that we won't pick something that is bigger than the query or the next query, right? Because the next query is bigger. Yeah, so that's pretty much the idea here. I hope it makes sense. Please leave questions in the comments if not. And now let's just implement it and make sure it passes. Okay, so let's implement the solution for this one. So what we need to do first is we need to, as we said, get the sorted list of queries. And we go through these. We go through these queries. Just do this like this, sorry. So for queue in queries, we want to have a heap that starts out with just the top left first value. That's what we said in the overview. And we want to give the indices. And we want to create a visited set which starts out with just the one that we already added to the heap. So 0, 0. and we want to keep track of the current count. That's what we did in the overview. And so here, while we have something in the heap and the the smallest value is smaller than the Q value here, than the query value, then we want to continue popping. So we do heap Q dot heap pop from H, and that gives us the value I and J. And so we increase our count because we just extracted something that is smaller than Q, so we increase our point. And then we go through the neighbors, and those are just using the usual traversal tap left, down, right. Okay, and we want to check that the coordinates are valid and that they are not in the visited set yet. Okay, because we don't want to visit again, and we just need to define here the number of rows and the number of columns. So that should be a simple something like this. And now we want to add to the heap. So heap Q push, heap push, and we want to push the grid value of a tuple of the grid value, of course, because we want to check that here. And so in I and G, and we want to add the coordinates as well because we want to need them. We will need them to get the next neighbors, right? So here we would pass in I and J. And now we will add to visited in I and J, right? Because we just visited them. Okay. Yeah, and that's pretty much it for the processing here. Now there is just one thing. What we want to return is an array of the counts in the original order, right? So for example, in this example here, the first example, the queries are like this, right? And we want the answers for each in the original order. But since we sort them to 2, 5, 6, we will get the answers in. So if I have maybe just counts array like this, and just each time add the count as we find it. So if I each time just do something like for this query, maybe counts, just append count, current count, right? For each query, I will get them in this sorted order, but we want the original one. So how do we do that? We can just make this a map from the query value to the count. So that way, even with this, we'll get 2 has maybe we'll get 2 has just 1, and we'll get 5 has 5 smaller than it, and then we'll get 8 has 6. Sorry, 6 has 8, right? And now we can just go and just fill these values up, right? Later on. So instead of using a list here, we'll use a map and just say for Q the count is this. That way at the end here what we can do is just say count for Q in the original query, not the sorted one, because that's what we want to return. Okay, so this is how we do it with this map. And yeah, that's pretty much it, right? Pretty simple, just a modification of BFS. So let's run it. So this needs to be HP. Same thing here. And here we want to push this to the heap here. So let's run this. Okay, looks like there is one problem on this. Let's call this for X. Oh, sorry, this should be in sorted queries, which is this one. Want to traverse in sorted order, and that should be it. Okay, so that passes and gets accepted. Yeah, so pretty straightforward solution. The main idea here is sorting and taking advantage of priority queue to just get the smallest value each time. Yeah, so that's pretty much it. Please like and subscribe, and see you on the next one. Bye.